All right, here we go. Good morning, good evening, good afternoon, everybody, and thank you for joining this Neo4j Live. Today we have a topic, a very interesting topic. It's called Aurendil, Future Graph Database Runtime, and I'm very happy to have James Clarkston on the show. Hi, James. How are you doing today?
Hi, Alex. I'm good, thank you. How's the weather over where you are?
The weather is mixed, I would say. I'm in Munich at the moment. It is was raining yesterday. It is now overcast. Little sunshine, a little mix. How's it where you are?
Exactly the same. We've just had a big pour down.
Yeah. Okay.
So I have to start that way because I'm British. So we always like to talk about the weather.
Yeah. No, but it's always it's a good topic to talk about the weather. You are James. You are a researcher at Neo4j. Senior Staff Research Scientist is your current job title here at Neo4j. What does that mean?
Yeah, that's a good question. I'm a senior staff research scientist, I think now. So I'm one of the members of staff that work in our kind of research group. So I work under Jim Webber. And I think over the last 4 years, we've slowly been trying to build out a research function within Neo4j. So the idea is that we try and do some work that is a bit more forward thinking. So instead of thinking kind of 6, 12 months ahead, we're kind of thinking 3, 5, 7 years ahead of product teams are. And the big idea is that we want to provide the product teams engineering with optionality and just try a few things that might be kind of on the horizon, some technologies that might kind of intersect with the products that we might want to consider. And sometimes we might find things that are really interesting and the product team should definitely use them in the product. But sometimes we might find things that actually, no, guys, don't go near this technology. So
skip.
Yeah. Exactly. So our role is to kind of sit in front of the product teams and kind of give them an idea of what technologies might be coming in the medium to long term.
Mm-hmm. Cool. So lots of AI these days, or are you already one step ahead?
AI is an interesting one because it's intersecting with pretty much everything we do. So traditionally, our research kind of group has come from a systems background. So my background is kind of supercomputing, hardware accelerators, GPUs, which is kind of quite lucky because AI all runs on that kind of stuff these days. So for me, I think the systems are changing, but they're not radically different to what they were. I think the use cases, how we're using them, is changing. So I think within the Aurendil project, already we started last year, and we're already trying to think about how the project might shift with respect to AI. And I think where it will change is in the application. And the thing is, people were doing different things with Graph to what they were doing kind of 1 year, 2 years ago. So it's still emerging. So we'll see how it goes, but I think it's quite exciting.
Yeah, it's a great time. We were just at We Are Developers last week, which is a big developer centric conference here in Berlin with 10,000 of developers, and we had a nice stand there, and lots of people come by, and it was very clear that lots of people were, or the majority of people, I would say, were interested in things of how to make use of AI, how to build something with AI, how to make use of it, and to be at the forefront of things, because we now have seen, I think, a little bit, everybody played a little bit with it, had the first disappointments of that it actually isn't what you wanted it to be, or that you thought it is more than more promised, I guess, than what actually comes out of it as a result. And then okay, but now what? But still, I want to make it work. I think it's a great opportunity here. But what do I need to do? And we had lots of GraphRag, obviously, discussions and conversations here. So it's going in the right direction, but it's definitely it's definitely some more work to be done here for sure.
That's it. But the good thing is it's all about disruption. I think the way we're using computers, the way we're using technology has just changed dramatically in such a short space of time that actually it's quite a fun space to work in, because there's lots of new things, new kind of doors opened up that previously weren't possible. So I think it's quite a fun time to get kind of be in the space.
Definitely. So today this is a little bit of a, well, not necessarily a very different episode, but it's a little different. Usually we have on the show some kind of a demo showcase. Somebody developed an interesting tool or something built on Neo4j, and then we give a bit of a background how this happened and what it can do, and then we show off a little bit what it actually does in a demo-like scenario. Today, obviously, we cannot do that, because you are in your team, you are researching things that are not really there yet, or you're advising more, or not, like you were just outlined before. So I think it's also a nice opportunity for everybody watching us live to ask questions about, what is it what is it you'd like to see in terms of what Neo4j should have, or what would you like to see from a database or from a graph database in the future, and where would you think the whole field or the whole technology may be going? So that would be interesting to hear from you, and I can relay obviously over to James any questions, any comments you have. So obviously let's engage. Let's keep it interactive, and try to have a discussion. But you have and Aurendil is you said it's the future graph database runtime. So you that's really down to what makes or breaks, almost, I would say, the product, I think, because it's if your runtime is slow, if you have an awful experience with this integral part of the database, I think that makes it very hard for people to use it. It's not fun. It's not performing. So it's a very hard, I guess, key technology bit in the whole Neo4j stack.
Oh, 100%. I think you've picked up on quite a few interesting points there. So I've been, but my background is kind of programming languages and kind of hardware. And one of the themes through my research is about how you make things accessible to people. So this is kind of why we kind of zoomed in on the graph database runtime, because like you said, it's one of the key kind of components that people interact with. And like one of the parts of the project that we want to kind of think a little bit about is productivity. And like if you break that down, it gets quite interesting, because people that use graph databases, they form a relationship with the tools they use. So maybe it's not just graph databases, programming languages, databases, whatever tools. You build up a relationship with it, and it can be good, or it can be bad, or it can be in the middle. And I think what we wanted to try in this project is to look at examples of technologies that have actually created positive experiences. So I think in programming languages, the trend has been to move to things like Python, where actually there's a really low technical barrier to entry. So everyone can go write some Python and kind of write some code and actually feel like they're productive. And that is quite an interesting feeling, because it turns out that lots of people write Python now, and it's probably one of the most popular programming languages out there. And it's just eclipsed everything else. Like the people that go into programming now, they probably won't start with C++. They'll go straight to Python because it's so friendly. So part of the work we want to do is say, well, why is Python so friendly? What makes it kind of a happy place for developers? And there's a few things that it does. I think the first thing is it doesn't explode in your face every time you get something wrong.
Always good.
So there's kind of a question about kind of, well, how do you do that in a runtime? And what we can do, what we're going to look at in the project is whether we can take some of the techniques that they use in programming languages and implement them in Cypher. So if anyone has kind of used Rust, that's a great programming language, because you write a program, if it doesn't compile, the compiler tells you what you've done wrong, and it suggests how you want to change your code. And then normally if you change it, it works. And then once you've got it compiled, your program runs. And that experience is so refreshing for people that have been come up on kind of languages like C++, where you make a mistake and you get pages and pages of error messages that you just can't decipher. So it's kind of like, how do we get that experience into Cypher? And the way we're going to try and do it is to lean on managed programming languages. So try and kind of integrate the system a bit closer with the graph, so that as you're programming your Cypher, it can check to see whether a label exists or whether it doesn't exist, whether two labels should be connected. And if they aren't, we can be a bit more nicer about kind of messages that come back. We can say, did you really mean to connect these two things? And that's the idea. I mean, this is part of the spiel that we put into writing the project. But since we put it in, and now I think LLMs have appeared, and they'll probably undo everything we want to do, because English will become the kind of de facto way you interact with databases. Maybe not English, but kind of natural language.
Natural language,
Kind of describe it. But and I think that gets a lot nicer, because once you're using natural language, like this, you feel more productive. You can just ask questions naturally. You don't have to learn a syntax. You don't have to decode error messages. You can kind of have that conversation, and you're in a much nicer space when you're interacting with the technology.
Yeah, definitely. I think that also is a great way of I think calling on our legacy as the query language Cypher, which always was or is always, you compare it with SQL and you see it's such easier to understand. It's such more approachable. People can even in a non-technical background, you show it a Cypher query to somebody and they say, hey, here, this is what we have, and does this make sense to you? And then people would say, yeah, let me look at this. And even if they have never seen a Cypher query in their life before, and if you explain them in 5 minutes what is what, they can understand what's happening here. And in, I think, most of the other languages, this is going to be a very, very big hurdle. So I think this approachness and this openness to make sense of data, make sense of that, and be approachable and be open. I think that's a great way. And then if then it continues, and getting error messages that make a little bit more sense to you, that you then understand better and then can help. And eventually, I agree, it's going to go into the direction of I don't need to know any query language or any programming language. Well, maybe programming language still, but maybe I don't need a query language for a database. I can just type it in, and then it's going to be translated into whatever the query engine is like, and then get the response back.
Oh, 100%. I think what's quite interesting is when I joined Neo, I think Cypher was one of the great things about the tech stack, for the reason you've just mentioned, that actually you can write really complicated queries just by literally drawing out how you think the data is connected. And I think that kind of fits into this theme nicely. So I think Jim kind of talks about the design of Cypher and saying that you have kind of round brackets and square brackets. And the idea is that the early kind of engineers that were working on Cypher used to kind of draw their queries in Visio. So they wanted to have kind of a syntax that they could draw on a whiteboard, distinguish between nodes, relationships, have the arrows to connect things, have it so that they can write it in ASCII art when they're typing on the keyboard, but also that it kind of fits into Visio as well. So it's kind of visually inspired. And I think that actually works really well. It makes it a bit more refreshing, because having that syntax means that you don't get bogged down in semantics and syntax when you're kind of learning the language. You can kind of draw what you think. What you get back might not be what you expect, but in the kind of most of the time you'll get something close to what you expect. And I think that's really good. It's a really, really positive kind of property of Cypher that I really like.
Yeah, definitely. So Aurendil, let's move over here, I think, a little bit and discuss that. What is it exactly? Maybe you can catch us up there, and I don't know, do you want to go through a couple of your slides, or
I can give it a go. So let me just try and share my screen. So let's see if this works. So there we go. So, I've got a couple of slides, so we can work through this. So I guess at the beginning, like I should probably say that big thanks to UKRI that actually sponsor the Aurendil project as part of the Future Leaders Fellowship Scheme. So
okay, cool.
We get kind of quite a high-profile project. So the idea, when I distill it down into kind of 3 points, is to look at a step change in graph technology. So the idea is that because we're in research, we don't want to think about something that is incremental, that we could implement it in 6 or kind of 12 months. We're really interested in technologies that will actually disrupt the space we're working in. So Aurendil is about kind of finding a step change in the technology. So we're going to try some really radical things and hope that some of them work. So that's the key point. The second point is that everything is graph-centric. So there's probably no surprise here, but what we want to try and kind of bring out more in the system is that graph should be kind of a first-class kind of citizen when you design every single part of the system, from the query language down to the storage engine. This is one of the things that existing systems perhaps don't do. They might have graph designed into one component or two, but not throughout the stack. So you get some interesting kind of trade-offs or kind of weirdness in how you interact with systems, because sometimes it feels like you're putting a kind of square peg in a round hole with graphs. And part of it is to kind of break that down and go, well, actually, could we kind of have graphs kind of percolate through the entire stack so that you get like a more natural integration with components? So that's the second thing. And then the final thing is, I think this kind of comes back to the AI talk, topic that we touched on at the beginning, but graphs seem to be important for so many applications right now that people are building really big knowledge graphs. They're just building really big graphs that they want to query. They want to kind of detect fraud in real time. They want to look at kind of, or I don't know, do complex analysis through kind of irregular networks. And one of the things we once set out to do from the beginning is to kind of look at how we get to the next level of scalability and performance so that we can enable these kind of future applications on Neo4j. So that's the kind of high level part of the project. So I guess this is my slide for people that if you've never heard of a graph database before, I've got my kind of, there's 2 things that you need to know when I'm talking. So the first thing is that Neo actually has graph native storage. So the key principle here is that instead of storing data in terms of rows, columns, tables, we actually store things in terms of nodes, relationships, and edges. So that theme of graph all the way down, our storage is a graph at the bottom. And the second part with Neo is that we're a database company, but our queries look different to everyone else. We don't do SQL, we do Cypher. Hopefully everyone knows that already, but sometimes these things have to be pointed out. So the first question is, how do we kind of produce a step change in technology? So what we did when we were kind of pitching the project and kind of starting out was to kind of go around and kind of survey the state of the union. And what we did was we looked at lots of graph databases and we tried to work out what trade-offs each of the systems were making. So I'm interested in two dimensions. So we've talked a lot about the productivity already. So to me, productivity is how difficult is this system to use. We can have a really fast system, but if it takes you 3 days to learn the syntax to some query language, then it isn't productive. So productivity is kind of, can we mutate graphs? Can we easily get answers to the questions that we want? So that's a productivity axis. But the other axis is performance. So this is how fast can we get our kind of answers? And you could think of that as kind of how many queries per second can we have, or maybe latency. And as a system designer, you have to trade off these two things. So nothing comes for free. So you have to balance these kind of two orthogonal kind of features. And it means that most systems will probably exist on this blue dotted line. So we went out and we had a look, and what we found was that actually there's kind of pockets of like interesting kind of systems all over the place. I think what I'm trying to show here is that those kind of pockets of systems share lots of commonalities, and they kind of broadly look like this. So we've got our kind of high performance, low productivity box in the top left-hand corner. And what is happening here is that we have people designing systems for graphs that are very focused on achieving maximum performance. What they typically try and do is reuse existing technologies. They want to use kind of very modern hardware to process these things, and they want to just get an answer as fast as they can. And then in the bottom right-hand corner, you have almost the opposite. You have systems where the idea is that they're a bit more user-friendly, so they let you mutate your data. You can change things. You have a bit more flexibility on how the system works, and they're probably a bit more expressive in terms of like query language. So you've kind of got those two corners, and in the middle you have systems that try and be good at both, and you get this trade-off. What's interesting is that I've got the horizontal line in the middle. To get over that, it's typically analytical products. So things like GDS, they get really good performance because they are so good at doing analytics that they just work really, really well for those tasks. But they don't support transactions, so they have problems when you're kind of want to change your graph, or your graph changes a lot. So you get a trade-off, and we're just saying that there's no right or wrong answer here. Like analytics products are really important, but they make a trade-off on whether they support transactions and whether they store things to disk. They might be in memory. So we have this trade-off space, and I think one of the interesting things that we discovered was kind of this side of the table, and this might be quite subtle, but we kind of discovered that this cipher here kind of ended up breaking a lot of these systems. I don't know what your cipher's like, but the idea here is that we're kind of connecting a person to a city, to a country, to a continent. And that sounds like quite a simple thing to do. But when the real world hits, you start to realize that actually, things aren't that simple because some countries are also cities. So we've got places like Singapore, Vatican City.
Yeah.
Okay, and that's interesting because it means that if we try and organize our data at the bottom too strictly, put it into kind of really strict buckets, then we lose our ability to connect arbitrary pieces of data, which affects our ability to model things in the real world. So this is quite a fascinating Cypher query that we quite like. So this Cypher and Vatican City is a problem for most databases at this side. And I think there's a bit of fun there, but the key thing here is that second point at the beginning where graphs all the way down, graphs everywhere. And this is an example of where systems are designed that don't necessarily think in terms of graphs. So they don't expect you to have kind of duplicate edges between nodes, or the flexibility to kind of connect arbitrary things, because they impose kind of some structure or ordering on your graph. And there's implications to that. So those systems might be fast, but they might not actually be able to model the real world like people want. So that was one of the fun things we found out quite early on. I think I got another slide where we kind of looked at the other side of the table. And I think here, the big difference between these kind of two kind of clouds was flexibility. So we see a lot of really flexible storage. So JSON kind of document stores that are actually really good at just taking whatever data you throw at them, and you can kind of link things together after. So they have no restrictions or very few restrictions on how you kind of connect things up, which is great. They end up being super flexible. You can put your data in and you can query it. But the problem is that they've kind of gone too user-friendly. So they've gone really user-friendly, but because they're completely unstructured, you kind of lose a bit of performance. So there was that. And then the other side here is the transactional side. So obviously when you want to support writes to your graph and kind of have strict guarantees about concurrent kind of access to it, then you naturally lose a bit of performance. So I think that those were two really fun bits that we kind of found out in our kind of background research before the project. And I think what happens is you start to see a spectrum of kind of things across this trade-off space. So on one side, we have a very static view of the world where people try and model graphs as tables, and we end up with really fast systems, but they're brittle because they can't cope with Vatican City. And then on the other side, we have a really highly dynamic kind of world where you can connect whatever you want together, but because they're completely unstructured, you lose some performance. And then with Neo, with Aurendil, what we want to do is kind of sit in the middle of those two worlds where we're not static, but we're not completely dynamic. So the big difference between what we're doing with Aurendil here is that we have an explicit graph in the graph storage that we can work with. The other two sides, they end up having an implicit graph. When you query your data, you have to reify a graph and then query that. Whereas in Aurendil, in Neo4j, the storage is just a graph that you can kind of traverse very quickly. So it means that we're kind of semi-structured. And because we're semi-structured, we can balance things on both sides. We're more flexible than being completely static. We have a bit of structure, so we can get some performance. And I think that's where we want to be. That's kind of a nice space to be. I think that was the first kind of bit of the talk. I mean, what do you think? Was that interesting enough? Or
yeah, no, that's cool, and I think that was always, when I talk to people, is when you have this option at Neo4j to be very, very free, and you say, okay, let's do everything you want and have no schema, nothing, and pour everything in. And the other side, you can be very strict at the same time and have a very concrete way of doing that with a schema. But I think the beauty is that you then it can work something in the middle where you have somewhat of a schema that gives you a little bit of a guidance, but doesn't limit you in a way of like the Vatican City problem. That's okay, but what do I do here? Or if you add something, or if you have then all of a sudden a new department maybe comes around and says, hey, I hear a new data structure, and you think, okay, but this was not part of the original structure, and now we cannot do it anymore because the whole system will fall over. But the graph has this flexibility to say, okay, yeah, it's fine. We just create a couple of new nodes. We add a couple of new entities that we want to have, and then we add them together. I think that's really nice.
Oh yeah, that's perfect. Like your graph evolves.
Yeah.
Business. I think that's a nice place to be, because like in a past life as a system administrator, and you'd spend forever kind of dreading when you had to upgrade a database. It would be the most painstaking kind of week or month of your life where you kind of try to preserve everything that you already have, back it up, put some new kind of structures in place, and then import stuff and upgrade the database. Whereas with Neo, things are a bit more fluid. It's a bit more flexible, where you don't have to drop the database if you change the schema.
Yeah,
and
exactly.
That's so amazing. And that comes from this kind of flexibility, the fact that the storage doesn't require us to kind of organize things in a specific way. So yeah, it's great.
How does Aurendil now improve on that? I mean, naively, I would say we already have this as a capability at Neo4j currently, and is that something, how fits in? How does Aurendil fit in there now?
Okay, so I think that's a nice lead into the next section where here I think what we want to do is kind of set out our stall. So how are we going to be different from everyone else? So we need to pick some things to be different about that is kind of not incremental, because we're looking for that step change. So if I kind of move on, I'll try and kind of articulate that quite quickly. So the picture now is kind of shows how Cypher is implemented today. And what's quite interesting is that the way that Cypher is implemented, it should be no surprise to anyone who builds databases, because it's a very standard design. And this structure of query language and its runtime, its execution engine, is what every single database does. Maybe not every single one, but it's kind of the standard way of building these things.
Okay.
And people have been doing it this way for years. Everyone reads the same book, they build the same components. And what you end up with is quite a kind of tightly vertically integrated system where the runtime system goes from Cypher. So it parses the Cypher all the way down the stack to executing the Cypher, and all the steps in between are kind of really tightly integrated. So this is how Cypher works today. And what we want to do with Aurendil is kind of mix this up a little bit. So what the first thing that we want to do is kind of drop some of this kind of traditional thinking. So the pictures, if you don't know who they are, so on the left is Cod. So he's very important in the kind of world of databases. And I don't know whether you recognize the guy on the right, but this is the inventor of Python.
Okay.
So part of the project is to try and move away from this kind of traditional kind of view of how we have always created databases, to try and adopt some of the thinking that exists in kind of the Python world. So one of the things that we've kind of talked about is kind of flexibility in schema. So one of the things that we want to try and do with Aurendil is to build a runtime that doesn't require you to upfront design a schema to optimize the system. So the idea is it's a bit like kind of a dynamically typed language like Python. You write your cipher, the system underneath will work out what should be connected to what. And if it finds an optimization that it thinks is good, then just applies it. But there should be no reliance on the developer to kind of put those rules in up front. The system should kind of discover it for you. So the way we do this is to try and borrow some techniques from Python, Java, JavaScript, where you've got languages that have been doing this for kind of decades. So that's the first kind of
that's a nice approach.
So that's our first kind of big idea. The second idea, I like my pictures. So if you kind of don't know who this is, so this is Lady Gaga, and she's kind of here to represent the fact that graphs are irregular. So when we look at things like social networks, sometimes your query might find someone that has 5 friends, but then every so often your query will find someone that has like 2 billion friends. And I think pop stars are the big kind of examples of this, where when you run your query, the system doesn't know how much of the graph it's going to explore. And we call that kind of irregularity. And one of the things that we want to do in Aurendil is try and make it so that the system can handle this irregularity better. So we know from the start that we're going to be running queries on graphs, okay? Because of graphs, we know that things aren't going to be regular. Things are going to be irregular. Some people will have 2 connections, some people will have 1 million. And the system needs to deal with that without kind of falling over. And some of the things that we're trying to do is kind of create a system that handles things like back pressure and kind of doesn't try and materialize everything. So these are important for things like scalability. So if we go to kind of 10x the size of the graph that we want to work with, then these are the important kind of system features that we need to kind of think about.
So you could you imagine it like a little bit? You know that this specific node has, I don't know, let's say 50 million relationship going out, but you would indicate that somehow, but you wouldn't just load all these 50 million relationships. So you just
So I mean, Neo4j already does that. So we already know if we are about to approach a node that has lots of relationships. So we have a concept of supernodes. But the key thing is that sometimes you have to process them. And if you have to process them, can we make sure that we do it reliably so that if we have to do 1 million kind of traversals from a single node, can we make sure the system doesn't fall over when we do it? So can we make sure that we do it in a given kind of memory limit and still make progress? And this is really important, right? Because if lots of people are using the database at the same time and one query takes up all the memory, then you starve everyone else. So there's kind of a question here about, well, actually, what can we do to make sure that people's queries don't interfere with other people's queries? And that's kind of what this idea is all about. We kind of know that this is going to happen with kind of 99% probability. So let's kind of think about it from the beginning. So that's the Lady Gaga problem that we're trying to think about. I think this kind of leads on to Aurendil. So the idea in the system is that we use a streaming-based approach. So instead of trying to materialize like big tables or intermediate results as we're traversing through the graph, the idea is actually we kind of define operations in terms of streams. And streams are quite cool because it allows us to kind of pause execution.
Yeah.
So here the idea is that we have a bunch of operators that want to kind of search through the graph, and they kind of have a work queue. So they have an input and an output queue. And the idea is that work comes in on the input queue, and then when that input queue is full, they can't accept more work. So because they can't accept more work, the person before them can't produce any more work. So it lets us deal with back pressure. And that's really important because it means that as these operators are executing, they fit in that really tight kind of resource, kind of memory limit. So we can ahead of time say, this query will have 200 megabytes of memory to work in. And this kind of stream-based execution model lets us work within that limit. The other thing is that it also lets us do things like concurrent execution. So here we're able to execute work on multiple operators at the same time on different threads. So we can do that. But it also lets us do parallel execution as well, where we can execute across all the things in the input queue at once. So it really opens up the possibilities for us in terms of kind of how we can schedule things on modern hardware. So all of a sudden we can work out of order, concurrent, and in parallel, which is good because those things help us with the goal of being more scalable and more performant.
Yeah.
So this might need a bit more explaining, but I'm going to leave it there because
no, I mean, we don't have to go into hardware details now, but I mean, you mentioned the beginning, let's move away from the 70s, and I think that surely also applies to hardware. I mean, we're not running on old CPUs and GPUs, and GPUs didn't even exist in the 70s, I guess. So I mean, there's new capabilities. The RAM is basically free. Well, not anymore now that DDR5 is making DDR4 so expensive, but that's going into another discussion here. But it's still relatively cheaper, and hardware is getting more and more powerful every time. So are you thinking about, and we can only cut this short, but would GPU powered graph database, not only visualization but really for querying, would that make any sense? Is that something you're looking at?
Oh, it's like you ask all the right questions. So it's such a good lead into the next section where we think about these things. But you're entirely spot on there. Like the world has changed, and this is kind of that theme of step change in technology. How do we get it? We talked in the last section about Cypher, like the way that the architecture of the runtime hasn't changed a lot in the previous few decades. So this is the core of what Aurendil is about, where we really experiment and we try a really radical new design in how we build these things. So this is kind of how we've broken down that stack so that we can do some of the things that you've kind of just mentioned. So if we kind of quickly talk about how we've changed the architecture, the idea now is that the architecture is a bit more modular. So what we've done is we've actually separated out the execution engine. So if you have a look at the bottom, what we have done is organize it so that the execution engine is scalable. So we have a hierarchy in terms of hardware. So we can have cores, threads, and tasks, which lets a scheduler sit and work out the best hardware resources to use. So this might be if you want to do a parallel query, the scheduler can kind of choose to use all the cores or one of the cores or some of the cores. But it also opens up opens up a path towards doing things like elastic kind of scheduling, where you start executing a query, and then if something is running slow, then our streaming model allows us to kind of allocate tasks to new cores to try and speed up maybe an operator that's taking a long time. And this is kind of that key thing that I talked about in the last slide about concurrency and parallelism. So this kind of execution engine is designed for high performance on kind of modern architectures, which is really cool. And the thing that actually sits above the execution engine is the runtime. So the key innovation that we've put here is that we've tried to integrate the runtime closer to the database. So the metadata service here, the idea is that this component keeps a track of the graph as you're building it, as you're mutating it. It knows statistics about what labels are in there, what types are in there, and kind of what are they connected to. So it should be able to answer questions like, if I end up on a person node, what other things am I connected to? And it should be able to say kind of a person will generally have 10 edges going off it, 10 relationships. 8 of them will be nose relationships. 1 will be a located relationship, and 1 will be maybe has an interest. That's the idea that with the metadata service. And next to it is the query cache, and in there we have some optimizers that actually work really closely with the metadata service. So as your query is running, it can inspect the metadata cache and rewrite itself so that the query can get faster or kind of make use of the information from the metadata service, which is exactly what Python does in the real world, what JavaScript does, what Java does. And essentially what we get into is kind of almost tiered compilation for Cypher queries. So what you'll see at the top is we have a front end. So the idea here is that you write your Cypher query, goes to the front end, has a quick kind of optimization. And then the first time you run it, maybe it doesn't work well because we don't know information about what the query is doing, what kind of types it interacts with. But the second time it runs, we can retrieve information from the metadata about the types it's interacted with. But we can also look at what has happened in that last run and kind of optimize based on history. So we can kind of get this kind of continuous improvement. So the more you run a query, the faster it gets is the idea.
Okay, that's clever. That's really cool. Yeah.
So we're trying to go quite crazy, quite radical here. And kind of go all out. So this kind of architecture opens up some quite interesting avenues for us. So I just talked about tiered compilation. So if we go inside the query cache, what you actually see is a couple of different paths into how we generate code from the query. So your Cypher comes in, it gets turned into this intermediate representation that kind of describes the semantics of a query. But we can't execute it necessarily. We have to turn it into a form that we can actually run on the hardware. And this is what this component does. So the first time we see it, we do some optimizations. But when we know that the query is running as fast as it can do, that we don't discover any new types, that it's kind of stable, then we've got this slow path in the background where we want to try taking that query, compiling it down into kind of machine code. And instead of having something interpreted, we actually just run some native code. And the idea here is that actually we get a big performance jump. So the more you run a query, the more information we get, the better we can optimize it. And then when we can't optimize it anymore, we turn it into machine code and it gets faster. So cool. This is one of the cool things that we're working on. I'll have to go through these quite quickly because there's a lot of interesting technologies we've got. So metadata-driven optimization. I'm going to not go into detail here because I've got an example later that's quite fun.
Okay.
Actually, here's the example. So the idea with metadata-driven optimization is that we can treat the Cypher query a bit more like a Java program or a C program and apply some of the optimizations that you would use in the programming language world in a compiler on the query. So what I'm trying to show here is that we have a Cypher query where we go from kind of forum to a person to a city. So the idea is that a forum has many members, and a person is a member of one forum, and a person is also located in one city. Now, the way that we execute Cypher queries at the moment is shown in the middle. So to kind of execute this, what we'd probably have to do is create a label scan. So we'd start at city because there's less cities than forums, perhaps. And then we'd have to traverse along the chain. So go from city, expand to person, and then expand again to forum. But when we have metadata, we can actually look at how things are connected. So in the table on the left, it kind of shows that a person is located in with degree 1, which means that this hop between person and city, there will only ever be one relationship here. So if we are only counting the results at the bottom, so this count star, that means that we're not actually interested in the result. We only want to count the number of results that we get, so we don't count out the values. That means that actually we can get rid of this one hop because we know it's going to be exactly 1. And if we traversing that edge doesn't actually change the output of that count, so we don't need to do it. So we can get rid of that traversal. And then we can also do a similar thing with the has member. So I'll kind of cut it a little bit short, but the idea here is that actually when you're left with forum has member person, then what you're actually looking at is the count of that has member relationship. And from our metadata table, we can tell that has member is only ever connected to forum and people. So we can just take a count of has member. So all of a sudden, the query had an execution plan in the middle. On the right, we turn it into kind of a single kind of lookup into metadata, which means we don't actually access any records to execute this style of query, which is quite cool. So this metadata-driven optimization, we're hoping will open up lots of avenues for improving the performance of like analytical queries on big scales. So this is quite cool. The execution engine, I think we'll skip over this because I've said a lot of it before.
Maybe if you have one more thing you'd like to really, that's really interesting or exciting.
Okay, so I'll share the results from kind of this month. So what we've been working on this month is looking about scalability. So different graph databases have different scalability properties. What we've tried to prove out in Aurendil is that all these radical changes that we've made actually work. So we've taken kind of one query that's triangle counting, and we've taken that query because actually it's a good test of different graph databases because it's so hard to optimize because the way that it gets executed, it normally explodes in memory. So the plots here, what they kind of show is that we have some graph databases. So there's kind of 2 strata for performance here. So we've got the ones at the top, and what you'll see on the right-hand side is that the lines kind of stop dead, and we've got a point. So what's happening there is that these implementations are just falling over because they don't have enough memory to execute this query.
Okay.
But at the bottom, what you can see in the kind of blue and purple line is Aurendil. So there's 2 lines. So they're both quite exciting. So the top line is a single thread of Aurendil. so single-threaded approach. And what we're saying here is that using our new streaming engine and our kind of optimizations, we're able to kind of move away from the pack in terms of where current graph database technology is, and actually produce a more scalable solution by quite a significant margin. So that gap between the lines is quite significant. So that's the first thing. So that's a single thread of Aurendil versus other databases. They can use multiple threads, so they're given the whole machine, and they still can't compete with Aurendil. The other line gets even more interesting, because what happens if you put a GPU in there? So the purple line at the bottom is the GPU accelerated version of the query. So all of a sudden, we're able to kind of improve performance just with the execution engine. But then we can have another drop, or kind of another leap in performance by using GPUs. And what you can see there is that purple line at the bottom is we get another performance boost.
Yeah.
What this means for people is even more exciting. So I've got two plots there. So I've got one plot on the right where systems kind of fall over because they run out of memory. Then the plot on the left where they don't. What this means is that we can actually run bigger data sets on smaller hardware. So on the smaller machine, we can scale to the same size data sets as on the bigger machine. And what that translates to in terms of kind of everyday users is that it's cheaper. The total cost of ownership of an Aurendil system ends up being significantly cheaper than other systems. I think the kind of sound bites that I like to use is that we allow people to do more science per dollar. And that's what the project's all about. So yeah, that's Aurendil.
Cool. That's pretty amazing and very interesting. The question obviously I have, and I think lots of people now have top of mind, is when can we see this, and is this and how is going to be this? Is going to be an addition to Neo4j, do you think, or is this going to be an evolution in terms of implementation, I guess?
Yeah, so that's a good question. So if we go right back to the beginning, so we're in research. So the idea with what we're doing with Aurendil is that we produce optionality for the product teams.
Yeah.
So we might build an amazing system, but how that gets into product might happen, and it might not happen. It might happen, or the product team might take the technologies in parts. So I don't yet know if, when, or how it will get into a product. But what we can do in the short term is talk about the potential that these techniques can have, and that actually it should be something that we look at for future products. So I think this stuff is pretty exciting. So I have to try and kind of talk to the product team and kind of find some friends there to kind of pull some of this technology towards the system. So that's what we'll try and do. The Aurendil project actually is a 4-year funded project. So we're UKRI based. So I think we've ended year 1. So we've got 3 years left. So we're still very much kind of in the early phase of the project. So not tomorrow.
No.
Hopefully in the future.
Okay. No, well, that's cool. I think that's really exciting. It seems very performant, at least here on these already after year 1, I guess. So I wouldn't be surprised to see this sooner or later in the product. I wouldn't be surprised if the product engineering team would be very interested. It's probably very interesting on what you're doing and what you're developing here, and that they want to put this in the product. And since it's already proving in this early stage that there is performance gains to be had from this. Yeah.
It's small steps. Like building a database is very hard. Like,
yes.
our engineering team do such an amazing job to kind of put the whole system together, that it takes like years to building changes like this. So I think both our big projects that happened recently, so we had our block store and we had a parallel runtime. Those were kind of multi-year projects from engineering. So Aurendil will probably be multi-year too. So yeah, these things are quite complex, but we can make a good case for inclusion, I think.
Definitely. Anything else you'd like to share? Is there any way people can be up to date with what you're working on, or with generally if people have maybe inputs or thoughts, or maybe some kind of feedback?
Yeah. So I think the best way to kind of stay up to date with the project at the moment would just be through the academic field. So we're a research group, but what we're going to try and do is disseminate some of this material to academic conferences. So that's kind of the first thing that we'll do. Then as we do that, what we'll try and do is reach out to people like yourself, like DevRel, and kind of trickle down some of these kind of technologies or kind of techniques that we're using into some more digestible forums. So as you can tell from the presentation here, we're actually got quite a lot of technical content that we want to kind of stuff into kind of a short amount of time, and perhaps that's not quite the best way to kind of disseminate it. So I think we're going to try and kind of get some papers out to the academics, and then slowly kind of come to developers and kind of find a way to get kind of engage with them. So I think I think following the DevRel team would be a good way to get kind of keep up to date with what we're doing.
Cool. No, that sounds great. I'd definitely be interested in hearing what's the progress, and see that come to the next stage for sure. So yeah, thank you very much, James, for this insight into what the research team at Neo4j is currently, or one of the projects the research team that Neo4j is currently working on, and little glimpse into the future, I guess, to what could happen, and what could be the future of the Neo4j runtime in a couple of years. So very, very interesting.
100%. Thank you so much for having me, Alex.
Absolutely, anytime. If you're interested in watching more in the future, we have a next stream scheduled already for the 22nd of July. So that's next Tuesday already, with Tomasz. Tomasz will talk about Essential GraphRag, which is the name of his book he just published. And it just came out, I think, this week. So very, very timely as well. And if you're interested in GraphRag and have any questions, any feedback, any comments on how to develop a GraphRag application, then this is definitely the event to join. So if you're interested in that, join us next week. Notes, the call for paper is over, but if you already wanted to get in and wanted to be informed about the latest updates about the conference that happens on the 6th of November, then use the link shown here. And if you are wondering what to do next, and if you want to use the current runtime that is working and implemented at Neo4j, you can go to Graph Academy to learn how Neo4j works from very fundamental to very advanced courses. But if you want to really get your hands on the product, try Neo4j Aura. No installation needed, or go to our community pages, Developer Hub, where you can find all the information about how to deploy, how to work with Neo4j, how to build with Neo4j, if any kinds of applications and drivers you would like. And if you are a Python fan, then we have drivers for Python as well. So you can just build using Python, and it's a relatively quick and easy start for you. And yeah, with that, I'll thank you all for watching. Ravi has said he's going to watch the next stream. Great. I'll see you then, Ravi, and everybody else, hopefully as well. Yeah. I think that's it for today. Thank you very much again, James, for joining today and for presenting. Thank you everybody for watching, and take care everybody. See you soon. Until next time. Bye bye.